Hi, this is AI with Justin. Hopfield networks are one of the oldest recurrent neural network designs, yet remain relevant, one, because of their historical relevance in unsupervised learning, particularly the development of the Boltzmann machine, and two, because of their similarity with biological systems, most notably the ability to act as a content addressable memory system and also its use of a local learning rule. In this video, I'll be explaining what an energy-based model is, how a Hopfield network uses a Hebbian learning rule to minimize its energy for stored patterns, and introduce the challenge of avoiding parasitic memories. An energy-based model is a probabilistic model governed by an energy function that describes the probability of existing in a certain state. The lower the energy, the more likely that state is. Hopfield networks are energy-based models whose inspiration came from the physical system of magnetic dipole interaction. Magnetic spin glasses are characterized by having a system of disordered magnetic spin states. When part of the spin glasses system is altered, the system as a whole goes through a reorienting process and eventually ends up at either the previous stable state or a new one. Hopfield networks have a state transition rule similar to this behavior. I'll return to this in a minute, but let's talk about Hopfield network architecture first. Hopfield networks are fully connected graphs. Each edge is symmetric and has a shared weight. Each node has an optional bias and a value that is binary, having either a value of 1 or -1. Note that this means it models only binary data. Okay, back to the state transition rule. Just as electromagnetism governs the stability of magnetic dipole states, the Hebbian update rule governs the stability of a given state in a Hopfield network. The Hebbian update rule states that if a neuron's activation matches that current neuron's value, do nothing. Otherwise, flip the bit. We've got a few terms to define here. The activation is the weighted sum put through a threshold of a neuron's inputs. The weighted sum is the sum of the product of each neuron's value except its own and the connecting weight. Let's go through an example where we calculate the weighted sum for neuron A. There are 3 outer terms for this calculation because A has 3 bordering neurons. Each term is the product of one of the bordering neurons and the weight that connects it to A. When we sum each term together, we get 3. This is the weighted sum. Lastly, the thresholding function sets the activation to either 1 or -1 based on if it's greater than or less than 0. To recap, the state transition rule for a Hopfield network is to calculate the weighted sum of inputs for a neuron, put it through a thresholding function, and if the output matches the current neuron's value, do nothing. Otherwise, flip that neuron's value. In this example, neuron A's activation matches its current value, so we do nothing. Let's continue onwards by calculating the weighted sums and activations for the other neurons, and determine if their values should be flipped or not. This process of iteratively applying the Hebbian update rule is referred to as evolving the network. In this case, we find that each neuron actually has an activation which matches its current value, so no values are changed. This means that the system is in a stable state and it must be at an energy minima. To calculate the total energy of the network, we take the absolute value of the sum of each of the neurons' weighted sums. In this instance, the current total energy is 0. Note that at each evolution step, the energy can never rise. It will only be lowered or remain the same. Let's initialize a new network with the same weights but different neuron values for nodes A and B. The network's total energy has risen to 2, and it's also now in an unstable state. Actually, every neuron's activation does not match its value. We could apply the transition to multiple or all the neurons at once, but this is discouraged, as it has the potential to cause infinite oscillations between states, and in fact, that's what would happen in this case. Typically, neurons are selected one by one in sequence or at random. Let's update neuron A for now. After flipping neuron A, the total energy for the network is still 2, but now it looks like only neuron B is unstable. Let's flip its bit. After flipping neuron B, we have now returned to the values from the original network. The network has evolved to a stable state by descending from a high energy state to a low energy state. So if we know that a Hopfield network will naturally evolve to low energy states, then we also know that if we can intentionally set a network's weights such that they minimize the energy for the states that we want to store, then other non-stored states with higher energy will evolve into those stored states. So how do we set the weights to minimize the network's energy for a desired state? Turns out it's pretty simple. If we want to save just one pattern, all we need to do is set the weights to the product of its bordering neurons. If we want to save more than one pattern, we just adjust the formula to take the average of each pattern's values at each position. These two videos show the same Hopfield network evolving to two different memories, one that looks like an A, the other an I. The network will evolve to either one of these patterns roughly based upon whichever pattern it happened to be initialized closer to in state space. Note that it is also possible for the network to evolve to an unintended minima, also known as a parasitic memory. I'll talk about why this happens and how to avoid it happening in my next video. If you enjoyed this video, please leave me a thumbs up and consider subscribing. Thanks.